Those famous photos of a quantum computer are mostly a refrigerator. The shiny chandelier is the cooling system. The actual processor is a thumbnail-sized chip hidden at the very bottom. Here's the simple answer up front. Quantum computers run colder than outer space because heat destroys the quantum states they need to compute. Thermal energy jostles qubits and scrambles information in a process called decoherence. To make qubits behave like qubits, engineers chill the chip to around 10 to 15 millikelvin, roughly 180 times colder than the cosmic microwave background. The machine that makes that possible, a dilution refrigerator, is as critical to quantum computing as the processor itself. Two fast misconceptions to clear away. It's not just because superconductors like being cold. Superconductivity helps, but the driving reason is to kill thermal noise so qubits don't fall apart mid-calculation. And that chandelier is not the computer. It's the life support system that keeps the computer alive. Think of a qubit like a coin balanced on its edge. Room temperature is a table full of small vibrations and bumps. The coin keeps getting knocked over. A dilution refrigerator is like putting the table in an ultra-still, ultra-cold vacuum chamber, so quiet that the coin can actually stay balanced long enough to do something useful. How cold is that really? Outer space is about 2.7 Kelvin. Liquid nitrogen is 77 Kelvin. Liquid helium gets you to 4 Kelvin. Quantum processors sit down at 0.01 Kelvin. In other words, it's not a bit chilly. It's a different regime of physics where random thermal kicks become so rare that quantum effects dominate. Now for the part almost nobody sees. The architecture that gets you from room temperature to millikelvin without breaking anything. These systems are built in stages, each one colder than the last. The outer layers are vacuum insulated to block heat coming in through air. Cryocoolers and liquid cryogens pull the temperature down to a few kelvins. Past that, the dilution refrigerator takes over and does the precision work, maintaining a tiny island of near-zero temperature at the very bottom where the chip lives. So what actually happens inside that dilution refrigerator? It uses a trick with two isotopes of helium, helium-3 and helium-4. At ultra-low temperatures, a mixture of these isotopes naturally separates into two phases. When helium-3 atoms cross from the concentrated phase into the dilute phase, they absorb energy. That energy is heat from the surrounding hardware. Pumps keep helium-3 circulating across that boundary, so the system continuously extracts heat and dumps it upstream. Put differently, every helium-3 atom that moves is carrying away a little packet of warmth, and millions of those motions per second keep the chip sitting at a few millikelvin. This is not like a kitchen freezer that just insulates and occasionally cycles a compressor. It's an active, always-on thermodynamic machine. Typical cooling power looks tiny, around a milliwatt at 100 millikelvin, falling to the 100 microwatt range near 10 millikelvin. Let that sink in. At the coldest stage, a fraction of a milliwatt is a mountain to climb. Why does that effort pay off? Because at 10 to 15 millikelvin, there isn't enough ambient energy to randomly kick most qubits into excited states. The probability of a spontaneous jump drops to below 0.1%. In that quiet coherence time, the window where a qubit stays in a useful quantum state stretches from microseconds toward milliseconds, or even seconds depending on the design. That's the difference between a toy and a computer. There's a concrete example seen in today's superconducting machines from companies like IBM. A typical processor with dozens of qubits sits bolted to the mixing chamber, the coldest plate, inside a dilution refrigerator. It takes about 12 to 24 hours to cool the stack from room temperature to operating temperature. During operation, control signals travel down long coaxial cables from room temperature racks. Those cables pass through attenuators and filters mounted at each colder stage, so the refrigerator can strip away heat step by step before the signal ever reaches the chip. Measurement signals coming back are whisper quiet, on the order of tens of femtowatts, so a special low-noise amplifier at around 4 Kelvin boosts them before they leave the cryostat. That control and measurement path introduces the next big challenge. Wiring is heat. Every cable is a tiny thermal bridge trying to smuggle warmth down into the coldest stage. 100 qubits can mean hundreds to over 1,000 lines for control, readout, and biasing. Most of the leaked heat is intercepted at higher temperature plates, but the residual load still adds up, and the dilution refrigerator has to continuously remove it. As systems scale, the cable count climbs, the heat load grows, and the cooling budget gets squeezed. This is where cryo-CMOS enters the story. Control electronics designed to live at cryogenic temperatures. Intel's Horse Ridge chips are one example. Put smarter, more integrated controllers inside the cryostat, closer to the qubits, so fewer cables need to cross from room temperature. Shorter paths can cut latency, reduce noise, and most importantly, shrink the thermal load that would otherwise overwhelm the cold stage. Scaling also pushes on the size and design of the refrigerator itself. IBM's Project GoldenEye explored an extra-large cryostat built to host and cool bigger quantum processors with more wiring and components inside a single system. Bluefors, a leading cryogenics company, has been shipping modular dilution refrigerators, like the KIDE platform, meant to support larger and more flexible payloads. The key idea is that cooling architecture, not just chip design, now limits how many qubits you can meaningfully operate together. There's a practical supply issue in the background: helium-3. This rare isotope is the working fluid that makes dilution refrigeration possible. Global supply is limited and tied historically to nuclear programs, so costs rise as demand grows. For a future where quantum data centers run many large cryostats in parallel, helium-3 management becomes a real bottleneck. Engineers are already integrating pulse tube cryocoolers to reduce reliance on liquid cryogens, improving recycling systems, and experimenting with alternative stages to stretch scarce helium-3 further. Power consumption is another quiet constraint. Moving heat from 10 millikelvin back to room temperature through multiple stages is energetically expensive. Facilities can draw tens of kilowatts of electrical power per system to maintain a cold stage that removes only micro to milliwatts of heat. Put differently, most of the energy goes into holding an impossibly cold oasis around a chip smaller than a fingernail. That brings up an appreciation moment. Keeping a processor colder than space isn't just science, it's orchestration. Vacuum shells suppress convection. Gold-plated thermal shields slash radiation. Vibration isolation keeps mechanical noise out. Electromagnetic shielding prevents stray radio waves from slipping in and flipping a qubit. It's a symphony of small defenses, all working so a sliver of silicon or superconducting metal can act quantum mechanically for a few milliseconds longer. As the field matures, the invisible details define what's practical. Cryogenic amplifiers at 4 Kelvin, for example, can make or break readout fidelity, and new devices are cutting heat dissipation dramatically, aiming to reduce how much warm hardware needs to sit near the cold side. Control software schedules experiments to spread thermal load in time. Even the geometry of cable routing through the cryostat affects performance. It's worth asking, do all quantum computers need a dilution refrigerator? Not necessarily. Trapped ion systems hold charged atoms in electromagnetic fields at room temperature, using lasers to control them with high precision. Photonic approaches use particles of light and can operate at room temperature or with modest cooling, around a few Kelvin for certain components. These paths sidestep the millikelvin challenge, but they pay in other currencies: large optical systems, complex laser stabilization, or demanding error correction overhead. There isn't a free lunch, just different engineering trade-offs. Back to superconducting platforms, where most of the colder-than-space headlines come from. The stakes are not just academic. Cloud-accessible quantum machines must stay up for users, but a warm-up or a maintenance event can mean a full day to recool before the next job runs. As fleets grow, operators will need redundancy, fast recovery procedures, and perhaps modular cryostats that can be swapped without months of integration. Picture a quantum data center. Rows of tall cryogenic enclosures, helium handling and recovery in the back, power and vibration isolation built into the floor, and racks of classical control electronics feeding signals across thermal boundaries. The business model depends as much on cryo uptime as on qubit count. One more nuance about temperature. Colder isn't a straight line to better. For many superconducting qubits, getting below roughly 1 Kelvin brings big wins because thermal excitations drop dramatically. Past that, improvements taper. Going from 100 millikelvin to 10 millikelvin helps reduce rare errors, but it doesn't multiply performance by 10. The simple version is, reach the regime where thermal noise is negligible for your qubits and architecture, and then optimize everything else: wiring, shielding, control, Error correction around that point. A few numbers to ground it. Operating temperature, about 10 to 15 millikelvin at the mixing chamber. Cooling power, roughly a milliwatt at 100 millikelvin, down to around 100 microwatts at the coldest point. Cool down time from room temperature, 12 to 24 hours. Readout signals, tens of femtowatts, amplified at 4 Kelvin before leaving the cryostat. And that memorable comparison. These chips run around 180 times colder than the background temperature of space. All of this brings the story back to a simple takeaway. Quantum computing isn't just about exotic physics on a chip. It's about conquering heat, vibration, and stray energy at every scale, so fragile quantum states can live long enough to be useful. The dilution refrigerator and the infrastructure wrapped around it are not accessories. They're the platform. As the field chases more qubits and better algorithms, the real breakthroughs may come from quieter cables, smarter cryoelectronics, larger and more efficient cryostats, and better ways to source and recycle helium-3. Put differently, the future of quantum power runs through the engineering nobody talks about. If this breakdown helped make the cold part of quantum computing a little clearer, consider subscribing for more fundamentals like this.